How are you?
Hello, hi John.
Hi.
Hello everyone.
Hi.
Glad to be here.
Nice to meet you.
Yeah. Thank you for inviting me. Yeah.
I'm glad you made it. I was feeling underprepared and was gonna suggest putting the entangled discussion up.
No, I was just quickly just doing some very last minute fine tuning.
So Helen, did you want me to do the introductions or did you want to do the intros?
Yeah, you can do the introduction.
Yeah, okay, cool. If you count me in when you're ready.
Sure.
So welcome to this Washington DC quantum computing meetup. Great to see so many people joining us today. And obviously, thanks to Deb and Helen for continually putting such a great series together. And it's a real pleasure to introduce today Dr. Daniel Oy from Strathclyde University to discuss with us the pathway towards a space quantum internet. So I think, if you break those words down into their constituent parts, there's a lot of exciting things there. I think when you combine them together, particularly with someone like Daniel explaining it and taking us on that journey, it becomes even more exciting. So we do, for those who are regular here, we do encourage interaction and audience participation, and I know that's something that Daniel also enjoys as well. And for those of you who don't know me, my name's John Barnes from Entangled Positions. So in the chat, if people want to put questions or comments, either to everyone or as the moderator to me, we'll try and incorporate that as much as possible. So without further ado, Daniel, welcome, and please take it away.
Oh, thank you, John. Let me just try to share my screen. This is always the most harrowing part of things. Is that working?
It is, yes.
Oh, great. Thank you. No, thank you very much for inviting me here. So just a little bit of background. So what I do. So I'm a senior lecturer at the University of Strathclyde in the Department of Physics. I'm a theorist, a quantum information theorist by training, but over the last decade and a little bit, I've been working on trying to take quantum technologies into space. So so this talk will be trying to sort of show what the end goal of this is. Where are we trying to head in trying to take quantum technology into space? And as we saw with the classical internet, with the internet that we have today, the applications and the revolution in how we do things, that was not really understood or appreciated at the time that these things were developed. So I would say that what we're trying to do at the moment is we're trying to build the tools or build the architecture or the foundation for whatever people come up, all the great ideas, all the great applications that people will come up with, having something like the internet but operating on quantum principles and allowing us to perform quantum information processing on a global scale. Right? So so this is so let me just make sure I can get my slides working. All right, here we go. So this is just a very short overview of what I will hope to cover today. I just want to clarify exactly how long do I have to speak?
You can talk for 2 or 3 hours.
Well, I'll probably won't talk for that long, but hopefully there'll be a lot of time for discussion. And as John said, if there's any particular question you want to ask at any time, let. I guess the easiest thing to do would be put it into chat, and then maybe one of the hosts can flag that for me to answer. So this is just a very broad overview of what I hope to cover. One is, what is the quantum internet? So, before we even get to space, we have to understand what we really mean by the quantum internet. I assume that there's going to be some basic background or knowledge in quantum computing and quantum information theory. But just to make sure, I'll just go over some of the very basics of what we mean by quantum information, entanglement, and how we use entanglement in order to do networking, quantum networking. Then I'll talk about, why do we want to go into space? Building quantum devices and quantum processors on the ground is difficult enough. So why do we need to go into space and put quantum hardware into space? I'll talk some about the challenges in trying to put quantum technologies into space, and I'll also talk about the progress that we've done in being able to develop actual hardware, actual missions, launch and operate things in orbit. So here on the right is an artist's impression of one of the very early concepts. So even though this article from which I've taken this diagram from is from 2009, the earliest ideas about using space for quantum communication really came in the 1990s, and then in the early 2000s, a European consortium looked at how can we do quantum entanglement experiments from the International Space Station. So this idea of using space platforms to perform quantum experiments is actually has quite a long history. So first of all, let's discuss what do we mean by the quantum internet. So for the purposes of this talk, I'm gonna very generically define it as large-scale distributed quantum information utilization and processing. So not just about computers, but when I talk about utilization, there are other things which are non-computational, which you can use distributed quantum resources. So not just network quantum computers. So we have a bunch of quantum computers here, and we want to network them. So we try to put some communication links between them. But we can also think of cloud quantum computing, where you have a quantum computer, but the user may not actually have their own quantum computer, but they can perhaps send quantum states to and from that quantum computer and do quantum computing by proxy. But you can also use quantum resources, quantum state communication in order to do things like distributed timing, distributed sensing. Obviously, we can do secure communications. Quantum key distribution is the main application there. But also, there are a lot of general quantum communication tasks where you can do certain distributed sort of communication tasks or processing tasks more efficiently if you have access to the quantum states that can be transmitted between different sites. One example is what's called the quantum Byzantine agreement protocol, which is shown to be much more efficient than classical methods of doing sort of like distributed reconciliation of databases and things like that. Now, the basis of the quantum internet is really dealing with the transmission and receiving of quantum information. So instead of bits, which is what we know is the classical building block of information theory, quantum information theory deals with qubits, the quantum bits, and closely associated with that, when we talk about communication, the thing that matters is the ability to create and distribute entanglement, quantum entanglement. And quantum entanglement, I'm not going to go very deeply into what exactly it means, but basically it's this non-local correlations between quantum systems. So quantum systems, even though they're separated very far apart, the quantum entanglement between them means that they are very strongly linked, much more strongly linked than you can describe just using classical mechanics, classical probability theory. And Einstein, dubbed this this very strong connection between separated quantum systems as spooky action at a distance. And we'll see that this that quantum entanglement is basically the building block in which we can actually build quantum networks. So qubits, just to remind everyone, these are the building blocks of quantum computation and quantum communication. Basically, these are controllable two-level quantum systems. Whoops, I think I got the order of my things wrong, so let me just go here. Right. So basically, what I've got up the top here, let me just get my pointer, my laser pointer. So here, right, this is a two-level quantum system. So it could be an atom where you've got a ground and excited state, but the important thing is that we can control it, and we can actually create a quantum superposition. So the quantum state psi here can be put into an arbitrary superposition of it being 0 and 1 with some amplitude alpha and beta. But when you measure it, if you try to measure it and see exactly what state it is, you'll collapse it into either 0 or 1 if, say, you measure it in the computational basis. Now, the important thing is that we can take qubits and actually put several qubits together, or put many qubits together, and instead of having a single state which is described in this form, in general you're going to get exponentially many different possibilities of what those qubits could be. So what we have is a very complex state, a superposition, an entangled superposition of exponentially many terms, which is exponentially complex to describe classically. And when we do coherent operations on these qubits, then effectively we are doing a simultaneous processing on all of those different possibilities. And really the key to quantum computation is that you have to be able to encode your problem in the sequence of operations you do, and you have to be very smart in how you extract that information, because when we measure it, we collapse the state, and it's how do you get interference between all the various different terms to get the actual answer that you want. Hopefully I don't need to say too much about that, because this audience hopefully has some experience of that. Now, there are many different types of qubits. There are matter qubits made of actual matter. We have atoms, ions, superconducting circuits, quantum dots. We can have impurity single atoms embedded within another matrix, so like nitrogen vacancies in diamond, or phosphorus atoms in silicon, things like that. But what we're usually, in communication, what we usually use are photonic qubits which are made out of photons. Either are mostly at optical wavelengths. Some people looking at microwave wavelengths for quantum communication. And so usually what we do is that we use matter qubits to do the computation, and we use photonic qubits to do the communication. There are exceptions to that. So there are photonic quantum computing architectures out there. And there are proposals for using matter qubits for actually transporting quantum information around. But in general, matter qubits is generally used for computation. Photonic qubits are generally used for communication. So let me just go back to here. Right. So now, if we want to, for instance, network quantum computers, then now becomes a bit of a problem, right? It's hard enough to generate and control large numbers of qubits within a quantum computer, right? You need lots of error correction. You need to do lots of error mitigation, lots of different things in order just to preserve the quantum coherence within the quantum computer. Now, you may want to connect two quantum computers together, because effectively you are basically making a much bigger quantum computer if you can connect two smaller quantum computers together. But in order to do that, you have to exchange quantum information, quantum qubits. And in essence, what we want is we need to be able to exchange or send quantum qubits, qubits between each quantum computer. However, if these quantum computers are located, any distance apart, then the communication channel between them is going to be lossy. right? If we send a photon between one place to another place, then there's a high probability that that photon, which encodes the quantum information, will be lost. And so, if we have our qubit and we try to send it over from one quantum computer to another quantum computer, there's a high probability that will be lost, and we'll lose that quantum information. Now, in conventional optical communication, say optical fiber, we're not dealing with just a single photon. We're dealing with large amounts of photons. These are very powerful pulses you're sending down optical fibers. And if some of them get lost, that's okay, because there's sufficient number of photons in order to make it. And you can also, if the losses are too great, you can amplify the signal. A classical information pulse, a light pulse, can be measured, and it can be then regenerated, or you can use an optical amplifier, and you can span very long distances with classical information. But quantum information is special because it cannot be cloned. You cannot amplify it, and you cannot resend it, because the qubit that the quantum information that you have, it is in essence unique. So I see there's a few questions here. So let me just see what we have here. So distributed timing, quantum information can be for such yeah. So in terms of amplification, so if there are things called quantum amplifiers, but there's a no-go theorem which says that you cannot amplify or cannot clone quantum information both with fidelity 1 and with probability 1. Right? You can trade off those two things, so you can sometimes amplify it and do it perfectly, but some of the time you fail, or you can always amplify it, but what you always get out is a degraded version of the quantum information that you try to amplify. So that's one thing. Why are photonic qubits considered over matter qubits for communication? Is it speed of transmission the reason? That's one of the reasons. Obviously, you can't go faster than the speed of light, so why not send light? But the other thing is that photons are cheap. If you want to send a matter qubit, you physically have to take that matter qubit from place to place. I mean, people have thought of this and thought of how can you transport quantum information around the world using error-corrected qubit on container ship. But generally, most people think about sending photons to send quantum information. So there's a question about how to begin with quantum communication. Is there a program for it? I'll talk about it later at the end if you want some resources. And so let's and there's another question about why can't we affiliate with other I think this question's actually gonna I'm gonna answer this because in the next slide, I think. All right. So let's go to here. Right. So what we have is the need for a way of being able to transfer quantum state between quite far separated say nodes on a quantum network, where we can guarantee that the quantum information that we want to send is not lost, right? And so what we can use is teleportation, but teleportation uses the resource of quantum entanglement. Now, the basic unit of entanglement is what's called an E-bit, or entangled bit pair. And we have a Bell state here. So this is a Bell state. You can choose one of the other Bell states, but it doesn't really matter because they all can be interconverted into each other. And we can represent this E-bit by 2 quantum bits. So Alice is one qubit, Bob is another qubit. And this line here represents that these 2 bits, qubits, are actually entangled. Now, instead of trying to directly transmit a quantum bit from one place to the other bit, what we can do is we can use teleportation, in that we can always do a repeat until success distribution of entanglement. So if we're able to try to send one half of an entangled pair, right? So let's say that originally Alice had both qubits, and then tried to send one qubit to Bob, so Bob had the other one. If this qubit never reached Bob, well, Bob just tells Alice, sorry, I didn't get that qubit. Can you send another one? And so Alice can keep trying to send entanglement, and until Bob actually gets the qubit. And now Alice and Bob know they have an entangled bit. So once they have this E bit, they can then do teleportation. So what we do is that Alice, she has one half of the entangled bit, but she has the state that she wants to send to Bob. Now, let's assume that Alice has no idea what the state is. She just knows it's a qubit, but it's some unknown quantum bit. So what she does a Bell measurement, and this is a particular type of entangled basis measurement. And she sends two classical bits, which are the result of that measurement, to Bob, and then Bob does a unitary correction. And then at the end of this process, Bob now actually possesses this original state. And in the process, Alice has conveyed this state to Bob, but at no stage do Alice and Bob actually know what the state is. So Charlie could be a third person who actually gave this quantum state to Alice. Charlie could go to Bob, pick up the state, and then he can check whether the state that Bob has was actually the state that he originally gave to Alice. So we can use entanglement. We can defer the actual transmission of a state until we are guaranteed an effective lossless channel, which is this channel is created by the entangled bit. And we can try until we get that entanglement distributed before we risk sending our quantum information. So at the end of it, Bob now has the state. Alice has destroyed the state in terms of the measurement that she did at the start, but Bob has the state afterwards. Now, the interesting thing is that we can not just teleport individual states, individual qubits, we can also teleport entanglement. Yes.
What would happen if they didn't wait for the herald, if they tried too soon?
Well, so you'd lose it, right? So basically, at this stage, right, let's say that Alice made the Bell measurement, right, but say Bob didn't have his qubit yet, and it got lost. Then Alice has basically destroyed her state, and then any quantum correlations that Alice and Bob are relying on, they've been lost because Bob has lost his qubit, right? Now, if say that Alice, say Bob actually did get the qubit after Alice did the measurement, then they can recover the state, right? So it's really whether Alice and Bob want to risk Bob not getting the entangled half of the qubit pair in the first place. Does that answer your question?
Well, I mean, Bob has a device, and he would take some action with it, and something would happen.
Yeah, that unique unitary correction depends on what the exact value of these two classical bits are, which are the result of this Bell measurement.
So he wouldn't know which unitary to apply.
Yeah. So if Bob doesn't know what these two bits are, Bob's qubit that he possesses is in the maximally mixed state.
And it's of no use
random.
whatsoever. Okay.
Yeah. So that's one of the curious things, is that Einstein, he really didn't like this idea, right? That you do something here and then something mysterious happens here, right? And then this unitary correction just basically corrects the state, right? So in one frame of reference, this state here was always in this state all the time, right? And then all you're doing is you're just basically doing one of four corrections to rotate it back to this state it was. Right? So in a sense, the entangled state encompasses all possible states that could have been teleported. And this measurement really just tells Bob, oh, how do you correct the state that Bob has so that it is the state that needs to be transmitted. I suggest don't think of it too much, otherwise you'll give yourself a headache. I mean, it certainly gave Einstein a headache. I mean, he didn't know about teleportation, but there's a very similar thing that he came up with Podolsky and Rosen, the Einstein-Podolsky-Rosen paradox, as it was called then, and it's all to do with what actually is happening under the hood, yeah. All right, I'll just continue. So let's see, where are we? All right. So the important thing is that entanglement can be teleported itself. So imagine this case where we have Alice and we've got Bob, and then in between we have 3 Charlies. These 3 Charlies, they're going to cooperate with Alice and Bob to get an entangled link between Alice and Bob. So if this is a very long distance where they can't directly send entanglement all the way from Alice to Bob in one go, if these shorter links you can create entanglement, then essentially, right, say Charlie 1 and Charlie 2, right, they've got an entangled link. So Charlie basically teleports this qubit over here, right? Now, it doesn't matter that this qubit is actually entangled with Alice's qubit. Essentially, what happens at the end is that now Alice and Charlie 2 are now entangled, right? And then Charlie 2 can then teleport this qubit to Charlie 3, and then Charlie 3 can teleport this qubit to Bob, right? So they do their Bell measurement. It doesn't really matter what order they do it. They can do it simultaneously. Charlie 1 can say, I want to go first, etc. It doesn't really matter. They do the Bell measurement. They send all of their measurement results, right? The 2 classical bits that for each measurement, they send it to Bob. Now, what we've done is basically we have not bothered doing the individual corrections, right? So if you think of Alice and Charlie, if Charlie teleported this qubit to Charlie 2, right, so that we have this entangled thing here, then ideally Charlie 1 should tell Charlie 2 the measurement result, and then Charlie 2 should do a correction on here, right? You don't need to do that, right? Basically, Bob just needs to know all the measurement results, and then Bob can just do the final unitary correction, which takes into account all of these classical measurement results. And then in the end, Alice and Bob have an entangled link, right? So this is called a quantum repeater, where we are essentially taking the entanglement in each link and we're swapping it. So the first step, say Charlie 1 does the measurement, then we're swapping the entanglement so that Alice and Charlie 2 are now entangled. And then if Charlie 2 does the measurement, then Alice and then Charlie 3 are now entangled. And then when Charlie 3 does his final measurement, Alice and Bob can then be finally entangled. So this is the basis on how you can do long distance quantum entanglement, right? So let's say that, imagine that it's very difficult to send entanglement directly, but you can make these short links, then we can basically combine these links into one very long entangled link. All right. So, all right.
I have a question.
Yes. Yep.
So if we're doing this with practical devices and we're sending photons, what kind of time delay would there be between when Alice tries to transmit the state and when Bob reconstructs it?
Well, typically, yeah, you're limited by time of flight, light speed. The next slide will actually probably address this. These are all good questions. These are all good questions because you're anticipating, exactly what I'm going to discuss. So I'll get to the next question, and maybe this will say something about tell you something about that. So the problem is that channel losses are still problematic in that you'll still have an exponential loss in fibers, right? So optical fibers have an exponential loss of, the best I've seen I could find was 0.14 dB per kilometer, or round up to 1.15 dB kilometer. Over 1,000 kilometers, if you're trying to send a single photon through an optical fiber, you will experience 150 decibels of loss, which is very large, right? You're not going to be able to send a single photon or half an entangled photon pair through that distance. Even if you have short links, right? So let's say we divide the 1,000 kilometers into 10 links of 100 kilometers long. Each link has 15 dB loss, right? But these Bell measurements that we're doing, which are basically swap the entanglement, these require that the photons, they arrive simultaneously at each beam splitter. Right, so within each Charlie, in doing the Bell measurement, there's a beam splitter where these two photons, they come in and they need to interfere. So they need to arrive simultaneously, and then you do your measurement, and then that is your Bell measurement. So that means that if you have these 10 links, each of 100 kilometers length, then you're sending photons along these links, and each photon needs to actually arrive for this whole entanglement swapping thing to work, right? This leads to an exponentially low probability that it would work, right? So if you lose any photon in this 1,000 kilometers, then you can't establish an entangled photon pair through this entanglement swapping process. So that leads to an exponential waiting time, regardless of the number of links that you divide up your, say, 1,000 kilometers. So what we need is a way of storing a photon until the other photon comes along, and then when both photons have arrived, have been stored, then we can do the measurement. Right. So we can then store the entangled photon pairs before we do the Bell measurement, and then this will mean that we do not get this exponential reduction in the rate at which we can generate entanglement. So it's exponentially faster to have all of the links ready. Then you can do all these Bell measurements at the intermediate nodes. Right. Let's see how this works. So we have a quantum repeater. So we have Alice, Charlie. So I've just simplified it into the simplest case where we've got one intermediate node and two sublinks. So Alice and Bob, they may be a bit too far that you can't really send a signal between Alice and Bob directly, but we have an intermediate node. So first of all, we have entangled pair sources. So these entangled pair sources, they generate the entanglement. They generate the entanglement that to be sent to Alice's quantum memory and to Charlie's quantum memory. So along the way, they may get lost, right? So Charlie basically waits until he receives a quantum bit, half of the entangled pair, and Alice, we assume Alice is very close to the entangled source, so there's no losses here. So that means that once there is an entangled pair generated, right, between here and here, Alice shuts off her entangled source, right? So this does require that Charlie and Alice, they need to communicate constantly, right? So when Alice sends the entangled, one half of the entangled pair to Charlie, she can't send the next pair until Charlie tells Alice yes or no, right? If Charlie says no, I didn't receive the photon you sent me, Alice can send another one. But as soon as Charlie gets half of the entangled state, Charlie tells Alice, I've got it. You can stop sending now, right? So Alice and Charlie, on their link, they can establish this entangled link independently of the other one. So Bob does the same thing with Charlie, generates an entangled link. Now at this point, we've got an entangled pair between Alice and Charlie and an entangled pair between Charlie and Bob. And then we can extract the photon from the quantum memory. We can do this this Bell measurement, and then we can transmit the information to Alice and Bob, and then Alice and Bob then will have their entangled pair. Right. So there is this communication overhead, and there's this time of flight delays which do come into the rate at which you can actually run these links. So in practice, what you would actually do is that you would actually have multiple memories operating in parallel. And so on one link, you can operate in parallel once one of those memories has established the link, and the other link, there's also been an entangled pair distributed. As soon as that happens, then you can do the Bell measurement and then establish a quantum entangled pair between Alice and Bob. So quantum repeaters are basically necessary, really, for any large-scale quantum networking. Now, there's been actually some very interesting and promising recent results where they've been able to establish small-scale networks, maybe like 3 nodes, so 3 separate nodes, and then they're able to, say, use Charlie in order to then swap between Alice and Bob. So it's on our way, right? This has been done on the ground using optical fiber, using things like nitrogen vacancies and diamond as the quantum memories, and so this is certainly on the path towards realization.
What was the distance they transmitted across?
I think there was some recent results which was like 10 kilometers, 20 kilometers, something like that.
Oh, that's exciting.
Yeah. So there's some questions here. Someone's explaining about entanglement. Sorry. Right. Yeah. Thanks for those putting in answering questions in the chat. So how does Charlie inform Alice that he has received the qubit? Yes. So this requires that what we have is what's called a quantum non-demolition measurement. So a QND measurement, a quantum non-demolition measurement, is you're able to detect the presence of the arrival of the photon, but you don't actually measure the state of the photon. And you just need to design your experiment so you can do that. So obviously we don't want to like measure the photon and destroy it in the process. You just want to be able to measure that it's arrived without actually destroying the information that's in it, the entanglement that's in it. How fast and read-write speeds of the state-of-the-art memories? So this is always the moving target. People are working very hard on these things. So the thing is that a lot of them are optically read-write, so they're actually quite fast. You're actually limited by some of the atomic processes occurring in it, but those things can be very, very fast. So people are thinking of gigahertz rates at which you could possibly run these things in parallel. So not necessarily each link is at a gigahertz, but if you're able to multiplex them together, you could get up to very high speeds. Yeah. All right. How much power? So the point of this is that we're not trying to replace the current internet, right? This would be a way of actually augmenting the current internet. If you want to network quantum computers, you need quantum channels, but obviously most of the traffic that we're still going to be sending and utilizing will be classical. It's just that there for certain applications we need this quantum channel, these quantum channels. All right, so John's put it 12.5 kilometers was the record last week. If Charlie is a hub with more connections than Alice and Bob, how can Alice tell Charlie she wants to start with Alice? Yeah. So basically, there's a. I'll get to this in the next slide. Density particles. All right. Well, yes, we can send over larger distances, but the rate goes very low. So do you need optical connections? You don't need optical connections. You could use radio for the classical communications if you want. It could be any sort of method of communicating, as long as the time of flight is lower than the storage time, right? These quantum memories are not perfect. They don't last forever. So that means that you have to do things fairly rapidly. All right, so let me just get on to the next thing, which answers some of the questions that have been brought up. So this whole concept of how do you build these large-scale quantum networks, and how do you coordinate quantum repeaters, how do you interface it with the classical internet? People have been working on this. So there's the Quantum Internet Research Group, QIRG, which is part of the IETF, the Internet Engineering Task Force. And so they have two main publications at the moment. One is the about application scenarios, and the other one is about the architecture that we need to build in order to build this quantum internet. These are mainly concerned with fiber-based networks, because this is obviously building upon the existing experience about building the classical internet, and mainly around optical fibers. So we've got things like, how can we interface matter qubits, the quantum communication channels, your classical communication overlay, the control plane, things like that. So there's actually quite a lot of work that's been done in trying to figure out how do you actually build this, how to interface it and build on top of what the classical internet, how it exists today and potentially in the next couple of years. There's a nice article in Science, in magazine Science, about the quantum internet, and goes into how you do this, how you use quantum memories and entanglement swapping, and how we can actually then do this. Okay, it's fully past. I haven't got to space yet. So, but great question, thank you. So why space? We've got these quantum repeaters, and they seem to solve the problem in that you can take the exponential loss over a certain distance by breaking up into smaller segments and using quantum memories. Sorry, was there a comment there? All right, someone just got to mute. Okay, so you're able to take an exponential loss and reduce that loss by putting these intermediate quantum repeater nodes. However, in practice, we may need to put quantum repeater nodes quite close together, right? So let's say 10 kilometers from this recent result, maybe 20 kilometers. If you want to go across the Atlantic, we're talking about hundreds of quantum repeaters. If you want to go halfway across the world, we're talking now maybe 1,000 or thousands of quantum repeaters. So this may not be practical, and may not be practical in order to span truly global distances. So quantum repeaters in optical fiber, they may be practical for, say, within a nation, within a country, within maybe Europe itself. But if we want to go really long distances, we need to find a way of reducing the intrinsic losses in the actual channel between nodes. So this is where free space transmission comes in. There's an exponentially lower loss if you try to send beams through vacuum. Now, in an optical fiber, you've got confinement of the beam so that a photon being sent in optical fiber doesn't spread out because it's confined within the fiber. In free space, a photon will actually spread due to diffraction, but that diffraction goes off, the reduction in the intensity goes by 1/r², the famous inverse square law. That is still exponentially better than exponential absorption within the optical fiber. Then you say, well, there's the atmosphere. Well, the atmosphere, let's assume a clear sky for the moment. It's actually very clear, right? In the optical wavelengths, except for certain bands, certain wavelengths where there's strong, say, molecular absorption, it is still fairly clear. Space is also the high ground, and that you can see a lot of the Earth, or you can simultaneously see lots of the Earth at the same time. And a single satellite can be seen by lots of places on the Earth at the same time. And also, if you have applications where you have, say, mobile nodes, such as like, trains or planes or ships, you can't run an optical fiber out to that. And there's certain applications where we do actually want to be able to have nodes to be mobile, right? So say GNSS, global navigation, or sensing, or time and frequency distribution. There are lots of places where we can't just run fiber out to where it's needed. So my other reason why I want to look at this and do wide scale quantum entanglement distribution in space is because fundamental physics and how to probe say the relationship between quantum mechanics and gravity, for instance. What's the next theory that will replace what we know at the moment, general relativity and quantum theory. We need to do bigger experiments. We need to have better experiments which probe quantum mechanics and gravity at scales and in regimes that we can't actually do on the Earth. And that means going into space. And these quantum links, the long-range quantum links, are going to be very important for many of these experiments. Therefore, if we are able to generate these quantum entangled links in space over long distances, this rising tide basically floats all boats. And one of those boats I'm on is how do we probe and test physics.
Somewhere I've seen the statement that it's impossible to construct an experiment that tests both quantum mechanics and gravity. Do you have any comment on that?
I don't know exactly what the statement was, the no-go theorem. Certainly there are regimes or scenarios where we can envisage where quantum theory and gravity interact at the level where one of them has to give. Now, normally that will be at very, very high energies, very very large curvatures. But the thing is that there may be phenomena at lower energy scales which give us some signposts towards what the next theory needs to look like. Theoretically, we are at an impasse in that there are so many possibilities on how we might be able to reconcile quantum theory and gravity. And it's because we are too unconstrained that it's been very difficult to have any progress. Once we're able to have the first hints of violations of the physics that we know already, right? I mean, from astrophysics, we already have dark matter, dark energy, or what, even if you don't believe in dark matter or dark energy, the observations are inconsistent with what we know at the moment, right? And that is a big that's a big driver to a lot of the theories that are coming up. How do we explain rotation curves? How do we explain the expansion of the universe, or the observations of the expansion of the universe? We need other bits of evidence which contravene the predictions of what we know at the moment. And once we get some more data, that will highly constrain what the theory needs to look like. Right? So it may be true that it's very difficult to get to a regime where conventionally quantum theory and gravity interact at the level non-trivially, but I don't think that means that we should not start looking, or we should stop looking for regimes where new physics might come up, right, which isn't predicted. Right. So that's at least my view on that subject.
Thank you.
Yeah. Okay. All right. So let's see. All right. Anyway, so there are other applications which involve quantum memories and quantum networks and things like that, which aren't necessarily computation or communication. So one is distributed timing. So there's a nice paper which showed how you could use entanglement to have a secure sort of global synchronization system. So not only do you use entanglement to enhance the timing accuracy and the synchronization amongst different nodes, but you can also use the entanglement to make it proof against spoofing or injection attacks and other things like that. You can use sort of quantum links to enhance things like gravitational wave detection, and also you can use entangled memories, quantum memories, in order to make distributed optical telescopes. So if you've seen the gravitational, the black hole images, right? So the images where they've taken lots of radio telescopes around the world and combined their data to be able to see black holes in the center of galaxies. So they did one of a galaxy which is far away, but actually the size of that apparent size of it was about the same size as the black hole in our own galaxy, which is now also imaged, right? That relies on the fact that radio waves, you can actually record radio waves. You can record the actual electromagnetic field of a radio wave, and then you can combine that recording later on and actually generate a large telescope, a telescope of the same diameter of that you've got your radio telescopes separated by. In the optical domain, it's very difficult to record directly the electromagnetic field of an optical photon. However, if we're able to store those photons in a quantum memory, we could store them locally. All right, you have your optical telescope, you store it into a quantum memory, and then you bring those quantum memories together into one point, and then you can then replay those photons back into an interferometer, and that interferometer will then give you the image with a resolution given by how far apart those optical telescopes were. So quantum memories actually have these applications which go far beyond just, say, creating entanglement for connecting quantum computers. Okay, so what is happening now? The European Union, they're working with the European Space Agency on what's called EuroQCI, European Quantum Communication Infrastructure. And this will be both fiber and space linked. So if they're going to use fiber for trying to do this, what they've already been trying to do, this quantum internet, this quantum networking, quantum repeaters. But also they want to use satellites in order to connect the distant reaches of Europe, of the European Union. They've got 2 satellites which are planned at the moment, I think, at least publicly acknowledged. There's Eagle 1, which is a pathfinder for doing quantum key distribution. And then the second one is to actually try to distribute entanglement from space to quite far separated points on the ground. And they want to do it for QKD, digital signatures, quantum authentication, clock synchronization, a lot of different applications. So that's the main big thing. Now, I highlight QKD because QKD is going to be the pathfinder application. Right? It's a quantum protocol which there are various grades of how you can actually implement it. At the very basic stage, you don't need entanglement. Obviously, eventually, if we use entanglement to do QKD, it becomes more secure. The assumptions you need to make about the security become less. And so, QKD is actually the way that we're going to start off trying to build these quantum networks.
I understand there are companies actually offering QKD service, but I don't know the range. I don't know if they have repeaters or what.
Yeah.
I've heard the Chinese have done something with this.
Yeah, I'll talk about that. So it'll be in the next slide, in an upcoming slide. So satellite quantum networking will basically be a way of linking up local networks, right? So you have these ground-based networks which can operate over a few kilometers, maybe a few tens of kilometers. But to link these individual networks, you will need something that can span these greater distances. And so we can see how the space quantum internet might evolve, right? It's sort of phased development. You can start with a single satellite or a few satellites acting in trusted node configuration, where effectively each satellite acts like a courier of secret keys. So it can establish secret keys between individual ground stations, say A and B, and then it can use what's called sort of key swapping. So it's a classical analog of entanglement swapping, but it's not really. It's just how do you take two individual secret keys and just generate one big secret, so one secret key where two different people now share that secret key. So this trusted node architecture, where you have to trust the satellite, obviously there are that security constraint doesn't work for everyone. I mean, if you're launching and operating the satellite, then that's probably an okay assumption. But obviously, you wouldn't want to trust that satellite to some company or other country that you don't trust. So what we want to go to is what's called an untrusted node, where, say, the satellite distributes entanglement down to these two receivers, and if the two receivers measure those entangled bits, then the non-local correlation within that entangled qubit pair can be used to generate an entangled, generate a secure key. So, so initially we're going to use non-entangled quantum communication. We're just going to send quantum states. We're going to prepare quantum states. We're going to measure quantum states, and the preparation and the measurement generate this secret key. But then we want to go to entangled state generation, entangled quantum key distribution, where you allow anyone to generate the entanglement, and you can verify that the states are actually entangled, and you can verify that the correlations that are produced are actually truly secret. And you can have lots of different configurations of how you set up the links and stuff like that. So we can have a single satellite down to two ground stations, or you can have a relay between satellites. So the big event, the seismic event in this area was the launch in 2016 of the Chinese satellite Micius as part of the QUEST mission, the Quantum Experiments at Space Scale. So this is a picture of that satellite. This is a picture of the satellite going across the sky and actually sending down a green laser beam, which you can see. The ground station is sending up a red laser beam for beacon tracking. These are just classical laser beams. These aren't the actual quantum states. And this satellite was it's about 635 kilograms, so say about half the mass of a small car. And it was in a low Earth orbit, 500-kilometer altitude, sun synchronous orbit. And as it went over China, it was able to distribute entanglement between two ground stations, which were over 1,100 kilometers in distance. The previous record of sending entanglement in free space was 144 kilometers, 143 kilometers. And to do that, this was in the Canary Islands, in the Atlantic, and they had to go on top of two mountains or two volcanoes in the Canary Islands, so they could actually see each other and get above most of the atmosphere, and then send entanglement between one node and the other node. And that was 144 kilometers. And this satellite satellite was able to break that record, you know, by an order of magnitude, basically. To send 2 entangled photons down, it sent about 6 million photon pairs per second. So it generated about 6 million photon pairs per second. These ground stations were able to simultaneously receive an entangled pair around 1 pair per second. So it lost, you know, 5,999,999 pairs for every 1 pair actually reached the ground. But that is much faster than if you had tried to put an optical fiber between these 2 places and try to send an entangled photon between those 2 places. Right? So even though, you know, it may seem to be quite inefficient, this is exponentially more efficient than if you try to use an optical fiber. The other thing to note is that they also did teleportation from Earth to the satellite. So from one ground station, they sent up an entangled state up to the satellite. They made this Bell measurement on the ground between another photon and half of the entangled photon. And they were able to show that the photon that was received by the satellite was actually, you know, in the right kind of state that they would have been able to do this teleportation. They didn't actually do this post correction, this unitary correction, but they sort of waved their hands and said that if we had done the correction, then we would have gotten the right state. And this is actually common in these kind of teleportation experiments that's been done so far. I don't think very many have actually done that full step of that unitary correction. Right. Now about quantum networks and fiber networks and what the Chinese have done, they have created an entangled, they've created not an entangled QKD. They've done a trusted node QKD network all the way down the country. So this is sort of representation of, this is quite an old picture, so it's probably expanded by now. But you've got metropolitan QKD networks. These are point-to-point links. And these metropolitan links are actually connected by long-distance fiber non-entangled QKD links. And then they use the satellite in order to connect you know, parts of the country where it's difficult to run these very long QKD links. So this spurred a lot of interest in the rest of the world. Now this is actually an old paper, 2018, and this is sort of some of the activity that was happening in the rest of the world, well, including China here. Germany, Italy's has a long-running series of experiments to do space communication to and from satellites. France and Austria have a nanobob project. Singapore, Canada, Japan have done some very interesting work trying to utilize conventional laser communication systems and try to do quantum experiments with them. There's interesting experiment with a laser comms terminal on geostationary satellite. This is just some of the more recent missions that have sprung up in the you know, after Micius had demonstrated the feasibility of satellite quantum communications. So I'm involved mainly in this project here and this project here. Also some involvement in these ones here. Large scale projects from ESA. There's this ESA QCI Saga, which is part of Euro QCI. NASA has some deep space quantum communication work, and China have started launching their constellation. So they're building up from their single satellite, which is Micius, and they've started launching smaller satellites to build up a constellation. Now, it's difficult to try to build these space quantum communication networks, right? So we've got these, the launch and space environment is a harsh one. Just getting into space is very difficult, you know, vibration, shock. In space, there's vacuum, there's radiation, there's thermal swings. that you have to design against. You have to make things operate autonomously, and that's one of the difficult things. Right? How do you take a science experiment in a laboratory and make it work unattended in a very difficult situation? How do you overcome the free space losses? So even though we're exponentially better than trying to do things in fiber, it's still quite lossy to try to send single photons over very long distances. The atmosphere is the biggest pain. I'll get into that. How to operate in daylight? Because we're trying to send, single photons. If the sun is in the sky, that's emitting a lot of photons, and those noisy photons can basically stop you from successfully detecting the photon that you're trying to detect. The satellites move very quickly, so you need to track them, and there's Doppler shift that you have to worry about in some circumstances. The amount of actual quantum states that you can actually send within a certain period as the satellite goes over the sky very quickly is limited, and actually there are statistical effects which now come into play. Very important for security purposes. And if we want to build large constellations and networks of these things, then how do we operate them together as a network? And also, we want to get beyond just quantum key distribution. We want to actually other applications before we get to full-blown sort of entanglement distribution or quantum networking. Building satellites, difficult. Size, weight, and power are the biggest problems. It's very expensive to launch things into space. It still is. It's very difficult to get the power you need and the volume, and develop these things to work. The environment is very difficult. So they've got these thermal swings every, say, 90 minutes. The very high vibration environment actually getting into space, and there's a lot of radiation that you have to deal with. The atmosphere is the biggest problem. If you want to do links between space and ground, you've got turbulence. You've got the fact that the atmosphere does absorb light a little bit, so you have to worry about that. There's scattered light from the sun, which can enter your telescope and ruin your measurements or your quantum states that you're trying to collect. And cloud and rain obviously are the biggest problems. So there's a very strong dependence on wavelength on the transmission through the atmosphere. So you can see the bits of the wavelength of the spectrum that are just terrible for trying to send signals through the atmosphere. You just choose a good wavelength. So some people go for 1550, which is the same as telecom wavelength through long distance fiber. Some people try in the near infrared range, which it's not too bad. It's only a slight reduction in transmission. You want to try to work in a wavelength away from the peak of the solar radiation so that you don't get scattered photons from that. We've been thinking of operating the UV as well, not just over in the infrared. And then even the night sky has actually light coming from it, because there's sort of photochemistry happening in the upper atmosphere, which can actually cause problems. Now, the biggest problem actually is going to be turbulence. The turbulence is the fact that stars twinkle, right? If you look at the stars, then they actually aren't just a very steady point of light; they actually all twinkle. And that's because the atmosphere it distorts the light, and it distorts it on a time varying in a time varying fashion, and that can reduce the efficiency of how you can get light from space down into a telescope. But there are adaptive optics that we can possibly use in order to correct that. Now, these things are typically very expensive, and so the main challenge will be to actually make this cheap enough to be deployable on a wide scale. There's system design considerations as well. You need a way of detecting the phase front error, so you need typically a beacon. It's not so bad as in astronomy, where you have to either use natural guide stars or artificial guide stars. You can use a classical laser beam co-propagating with a quantum beam in order to act as a guide star. So there's another question about JP Morgan needing yeah, well, so actually a friend, a colleague of mine has joined JP Morgan to lead their quantum security group. It's due diligence, right? They need to know, is it a threat? If it is a threat, how do they mitigate against it? So we actually know quite a lot about the space to ground optical channel from the Micius satellite. So this is a typical overpath. So these two curves are the ranges, the distances between the satellite and the two ground stations. This is sort of the total length here in this thing here. And this is the loss, right? This is the combined loss of these two separate optical channels. And you can see it gets down to, about 60 dB, just a bit below 60 dB. So 1 in a million, right? 1 in a million chance that both pairs, both photons of the pair of the entangled pair actually make it down to the ground station. But it is much, much better than fiber. So you can compare it to fiber. So over 1,000 kilometers, then the free space channel is much lower loss than if you tried to do it using fiber, right? It's just massive difference. Yeah, so that's that. How do you actually do SAT-QKD? Well, you need large optical apertures to reduce this diffraction. So the bigger the telescope you can use to send your beam, the narrower that beam will be when it gets to the ground. Obviously, the bigger this telescope on the ground, the more capture area you have, the greater the probability that you will actually collect the photon that's being sent from space. We want to miniaturize the pointing systems and potentially adaptive optics, together with coarse pointing systems. How to make those work well, and how do we synchronize the sending and arrival of these photons? That's actually quite challenging because the satellites are moving very quickly across the sky, and we need to account for every single pair of photons. So we need to know whether they're lost, or if they are simultaneously received. We need to know that one event of one photon arriving corresponds to another event of the other photon arriving. So how do you synchronize all these events? Right. I've been going for more than an hour. Do people want a break? Or should I just keep on going? All right, keep going. All right.
I think that's the consensus.
I'm fascinated.
Okay, all right. Now, lots of great comments in the chat as well, I can see. All right, so this is so now I'm just going back a bit in time. So this is to about 2010, 2009, 2010 is where I started looking at how do we put this thing into space, these kind of things. So I've collaborated a lot with the Center for Quantum Technologies down in Singapore, and with Alex Ling, who's a professor there. And we had the mission, our initial mission was, how do we take what would take, a whole optics bench and miniaturize it and try to launch it into space, right? We've got some early publications on what we wanted to do. We came up with a mission proposal, which we sent to the European Union Commission. They didn't actually fund it, but along the way we learned a lot, right? So initially, right, we want to take an entangled photon pair source, which in those days took up a whole optics bench, lasers and band conversion crystals and compensation crystals and lots of other optics in order to separate the photon pairs and make sure they're all entangled and miniaturize it. So we're able to make these very, very small. So this is actually 10 by 10 by 3 centimeters, I think. Or a bit smaller than that, actually. It's not quite 10 by 10 centimeters, it's about 95 by 95 millimeters. And so we're able to build these things and miniaturize it, but then we need to make sure that these work in conditions which are not ideal, right? Not in a nice air-conditioned, temperature-stabilized, vibration isolated experiment. So we hooked up with a friend of ours who actually launches these high altitude balloons. And he does it as a hobby. Yeah, he puts radio transmitters on them, launches them into the sky. They go to 130,000 feet. Go tens, if not hundreds of kilometers. You track them down and you retrieve them. So we put one of our early devices on it and sent it up to the space, and we found, well, near space, right? I mean, it's still only about 30 kilometers, 30 or 40 kilometers up in altitude, much lower than say 300 kilometers, which is sort of low Earth orbit. But still, we're able to demonstrate it works in this extreme environment. The next thing to do was to actually try to build a space mission, an actual payload. So then we were able to hitch a ride on this satellite called GOMX2. They had some spare space, they had some spare payload area, which we then inserted into. So this whole thing is only 20 centimeters from top to bottom. So we were able to be here. And then we tried launching it in 2014, I think. So here's, hopefully this will play. Let me just see whether I can get it to play. So this is launching to the International Space Station on a cargo ship. From there, it would then be put into orbit from the International Space Station.
That main engine's at 108%.
Yeah. So that was our first attempt to get into space. It wasn't great. Now, the amazing thing, despite that huge fireball, the cargo capsule was actually recovered a couple of days later on the beach. They're able to take the cargo out, which included our satellite, and send that cargo back to whoever wanted to send it to space. So they sent GOMX2 back to GomSpace, the company, and they're able to actually boot it up, and it worked perfectly, including our experiment. And so the experimentalists involved, they actually posted an April Fool's paper, which wasn't really an April Fool's paper because it actually occurred, about how we were able to do, very rigorous environmental testing on the ruggedness of our source. It is hoped that future launches will not provide opportunities to investigate this further. So it shows you that if you take care, you can actually make these, what is thought to be very delicate and fragile quantum technologies quite robust. So about a year later, just over a year later, we're able to rebuild an experiment. We didn't reuse the payload. We built another payload and put that on another satellite. This time, this satellite was built by locally in Singapore, at National University of Singapore, and it worked. It worked perfectly. We got all the results that we wanted. We're able to monitor it. It showed that we're able to generate these correlated pairs. They are entangled, but they're not entangled in the way that we wanted. I mean, we designed it so that they would be correlated in polarization, but not necessarily entangled in polarization. So this gave us confidence to build the next version, which would be the fully entangled source. So this is the SPEX2 is the name of the source, and Spooky1 is the name of the satellite. So Spooky1 was built by the actual experimenters building the entangled source. So we went from using someone else's satellite, satellite and putting a payload onto it, to building our own satellite and putting our own payload on it. So we're able to use a bit more space and a bit more power and a bit more mass. We refined the design so that it gave you fully entangled polarization, entangled photons. and we're able to launch it. So we launched it using via the Japanese space agency, JAXA. So they had a cargo ship that sent it up to the International Space Station. Here it is in Japan. This is being loaded into its sort of cargo pod, which was taken up to the International Space Station. It was put into what's called sort of like the space cannon. This thing here, it's got a lot of spring-loaded boxes in it. So it's on the end of an arm, and so it's brought into an airlock. The astronauts would take these boxes with spring-loaded mechanisms and put them into this unit. They swing it out into space, away from the space station, and then launch each of the satellites out into space. So this is why it's called the space cannon. And this is the satellite making its way into orbit, into a separate orbit to the International Space Station. We tested it. It showed really good entanglement. So these are visibility curves for anyone who's familiar. Able to violate a Bell inequality by several standard deviations. And it re-entered the atmosphere just over a year later, a year and a half later, or something like that. So this was very successful. We learned a lot. We learned that we could build a rugged, entangled photon source that could work in orbit, and it worked up to the very end. The other thing that we're able to do is actually investigate how radiation affects the experiment. On board, to test that we've got entanglement, we've got two photodiodes, single photon detectors. So these are silicon avalanche photodiodes, which detect the single photons, and we've got a polarization analysis unit, which allows us to detect the correlations in polarization. And if those correlations violate a Bell inequality, then we know that we are generating entanglement. But these silicon avalanche photodiodes, these have what are called dark counts. So sometimes they give a signal, even though no photon actually was present. And these dark counts, they get worse the more radiation damage these silicon photon diodes receive. Basically, the radiation, they can cause what's called displacement damage and cause defects within the crystal lattice, the silicon crystal lattice, and these can cause charge traps and basically can cause breakdown of the semiconductor at a much higher rate than if it was less radiation damage. But we're able to basically show that the placement of these avalanche photodiodes within the structure of the CubeSat actually had a significant impact on how much radiation they got, and therefore how much they were damaged. So in the next experiment, in the next set of launches, missions, we will actually want to test how can we best shield these very sensitive devices by different materials, different thicknesses, different placements, and stuff like that. So we're learning a lot from these small missions. This weighed 2.6 kilograms compared to 300 times more. Micius weighed 300 times more, but obviously we can't do as well as Micius, but our budget is correspondingly much smaller than theirs. So these kind of small missions, these kind of small satellite missions, there's a lot of other ones that sort of I'm involved in. There's a UK-Singapore bilateral mission, which is sort of the next iteration, where we want to send one of those entangled photons to the ground and keep the other photon on board the satellite and measure it. So we want to show that entanglement can be distributed from a small satellite from space to the ground. We're not trying to store them or anything like that. We're just going to measure them and then show that the correlation in those measurements could only have come from entangled photons. There's the UK Quantum Communications Hub mission, which also is very closely related to this UK-Singapore bilateral mission. Working on a commercial mission which doesn't use entanglement but uses what's called prepare and measure PKD. from a smaller satellite, so it's actually half the size of these two satellites. Also working with the Canadian mission. So Canada have a slightly bigger satellite, sort of a microsatellite, and they want to do uplink, but they also want to do downlink. And sort of they all come from, well, these three missions, certainly, these top three missions come from a proposal that we put into the European Commission a couple of years ago. So in the UK, so just to go very quickly about some of the stuff that we've been doing. So we've been trying to make these quantum communication systems as small as possible so that they can fit on very small satellites. So the biggest thing is, one of the big problems is how do you send these single photons over long distances? You need to point very accurately. You need to have a large optical aperture. So solving the pointing problem is one of the key things that we're working on. How do you design the entire system? Right? It's now not just an experiment that you do in the lab. It's something that has to operate in space, has to operate autonomously, and it has to be reliable, and everything needs to fit very neatly within a very small package. So 3D printing for mocking up things, system architectural design, and that has culminated in what's called the ROCKS mission, which Craft Prospect, which is a SME, a startup within Glasgow in Scotland. They are building a small satellite. So this is about the size of a bread bin, maybe a shoebox. So it's 6U. It's 10 by 20 by 30 centimeters in size. Got a space telescope in it, and it's got a very small transmitter. This is sort of a developed version of that. So that's the transmitter here. So this is the actual transmitter unit, and then it's got the control electronics around it. We've got a telescope with an acquisition, pointing, and tracking system in here. It uses a micro mirror, a small tip tilt mirror, in order to actually fine point photons. We've developed it from some early concepts into something a bit more engineered. We've had to design the telescope, which has then been built by the Fraunhofer Center for Applied Photonics. So this has been very rigid. It's athermal, so it will operate over a large temperature range, and it's got near diffraction limited performance over a 0.5 degree, half degree field of view. We've miniaturized the source. We originally used a source developed by Bristol University, which was handheld. So it's actually quite interesting that a lot of the technology, a lot of the ideas came from trying to build a quantum key distribution system which could fit, say, within a mobile phone. A lot of that miniaturization, a lot of those ideas have actually been expanded into how do you now send QKD signals over tens of thousands of kilometers rather than over a couple of meters for a mobile phone application. We've developed the concept a bit, but still it's a very small transmitter. This is not entangled as I mentioned before, but certainly you could try to replace that with an entangled source. A satellite transmitter is no use without a ground receiver if you want to do sort of global QKD. So we've been trying to build a mobile ground station. So here's a 43 centimeter or 17-inch telescope on a alt azimuth mount with lots of optical components on the back of it. This is sort of the system diagram. And we've been using this to try to build it up so that when we do launch the satellite, we have got something to talk to on the ground. So we can try to do actual QKD transmission. Testing it. So here is a panorama, a 360 panorama of the International Space Station going across the sky. So it sort of pops up into the sun. You can see the reflected sunlight and then goes back into the Earth's shadow. And we were tracking it with this telescope. We've been actually doing tracking experiments on Starlink satellites, and we can track them to within, say, 1 miliradian, but we need to get a much better pointing. So we use a fine pointing mirror within the telescope back-end optics in order to get the microradian tracking. And we've done some tests on the ground where we can sort of transmit over a couple hundred meters quantum signals and actually generate QKD signals. Now, ultimately, we need to be able to put all of these things together, not just a single satellite, but many satellites, and get them to work in a coordinated fashion so that we can actually service lots of ground stations around the world. All right. So actually, let me just go through the chat again, see if there's anything that I should say. Let's see. Yes, QC. Yes, so yeah, NASA's got some deep space quantum comms stuff, a lot of superconducting detector work, a lot of proposals for doing entangled experiments with the moon or with a satellite, with a space station near the moon. Yeah, people have thought about putting quantum computers in space. Could you use quantum computers to speed up some things that are useful to be sped up, at the edge of the network, like edge computing. Occurrence time of entangled photons. Entangled photons can go very, very far and still retain their quantum coherence. Basically, no one's really measured anything significant, even through the atmosphere. Quantum, entanglement's pretty robust as long as the photon gets there, right? Obviously, if it's absorbed, then you lose it. But if the photon does make it through, space or make it through atmosphere, the entanglement's actually preserved quite well. So there is a cold atom lab on the International Space Station. So cold quantum is mentioned here. It produces Bose-Einstein condensates, which are very useful states of matter and possibly could be used as a quantum memory. So actually, the cold atom lab and the replacement to that, which is called BECAL, BC cold atom lab, which does actually a lot more. I mean, cold atom lab does do BCs, but the BECAL will actually do a lot more. These kind of things are kind of things that we want to use, for instance, for doing quantum memories in space. SPAD damage. So we usually use silicon because they're cheap, right? You can use, say, indium gallium arsenide for the longer wavelengths, but their performance is typically not as good. Dark count rate, quantum efficiency. There's been a bit of a germanium on silicon to get that longer wavelength sensitivity, but with all the advantages of silicon fab. But yeah. Entangled photon paired emitted parallel. Yeah, so generally entangled photons are generated simultaneously. USA in terms of space quantum internet. Nothing, not very much that's actually publicly available. Who knows what's happening behind closed doors? But the US is being pretty lukewarm about QKD. So I think maybe the Department of Energy is about the only major US department to actually have anything really in QKD networks. And QKD networks are really the starting point for building much more advanced networks. I think the drive in the US has been more on the quantum computing front, and obviously when you're talking about networking quantum computers, then yeah, naturally we're gonna talk about quantum internet. Yeah, I might get back to the quantum repeaters later. All right. Yeah. Okay. So some terminology insertions are controversial. Well, I don't know. Well, we can talk in the discussion. Satellite constellation. So we need to be able to build these constellations. We need to operate it. So I'll just go quickly some of this. So basically, there's some projects working with Airbus, looking at, and a lot of other companies, to how to build these space quantum networks. Multiple layers, these different layers do different things. We have looked at a particular use case where we wanted to have a quantum key distribution network to aircraft. So we've got an aircraft, and it could talk to low Earth orbit flying satellites. So these satellites are here. These blue cones are basically the footprint over that these satellites can actually generate a key. Then oops. So, yeah, so basically your aircraft can talk to one of these satellites, generate a key, and then these low Earth orbit satellites can then relay that key to a higher ring of satellites. So these relay satellites, this relay layer in this sort of orange gold, this basically has inter-satellite links which then allow you to relay that key all around the world and then down to the ground. So yeah, these are going to be the starting point to how we build large-scale space quantum networks. If we want to use entanglement, then we have to then think about how do we use quantum memories. So space-borne quantum memories. Now, this is the Micius situation. We have an entangled pair source, and you've got 30 dB loss, for instance, on each downlink, right? So together, it's 60 dB loss. With the quantum memory, basically, we're just down to now 30 dB loss. That means it's 1,000 times more efficient if you're able to put quantum memories onto the satellite. We've gone through the entanglement swapping. So basically, instead of from 6 million pairs per second going to about a hertz, for instance, right, we could go down to kilohertz rate if we're able to use quantum memory. Now, earlier I mentioned there were these ideas about using matter qubits for transporting entanglement. So here we go. So basically, we have containers. In each container is basically a lot of error-corrected qubits. So we've got lots of basically the quantum computers which just don't do anything other than just error correction. And you could ship this across the world, and then you would then, if you load entanglement onto these things, and you have the corresponding entangled halves stored in the home port, then basically you're able to ship entanglement around the world, and you could store a lot of entanglement in each of these containers. So that's just a wild idea that a friend of mine came up with a couple of years ago. So now the reason why we want these spaceborne quantum memories is that you get much better scaling, right? So let's say let's look at this one, right? So this axis is the time it takes to generate a single entangled qubit. The top line is basically let's see, if you try to was it A to let's see, top beam, yeah. So basically, if you use different ways of operating your quantum memories, you can actually increase the efficiency quite a lot, right? So it's several orders of magnitude if you're able to design your quantum memories more efficiently. What isn't plotted really is what happens if you try to do it with fiber on the Earth. And basically, those lines are up here, right? It takes a long time in order to generate any entanglement over, say, 20,000 kilometers. Now, 20,000 kilometers is actually halfway around the world. So that's about the longest distance that you need to generate entanglement. But, basically, we're talking, years to get a single entangled qubit if you use quantum repeaters and optical fibers, because you have so many repeaters in an optical fiber repeater train that goes halfway around the world. That using these satellite networks, using quantum memories, is actually a lot faster. Now, it's not easy. The main thing is that a lot of these experiments, a lot of these quantum memories, for instance, this 1 hour quantum memory, these require cryogenic cooling. Now, cryogenic coolers in space, they've been done, but it's something that most space engineers will run a mile if you say you want to put a cryogenic cooler in your payload. So making them small, reliable, relatively cheap compared to what currently is available, is that going to be a big challenge, because we do need these very low temperatures in order to get these high quality, long coherence time quantum memories. The detectors, so we're going, I mean, there's a lot of work and there's a lot of push towards superconducting nanowire detectors instead of using avalanche photodiode. They've got a lot of advantages, not just the efficiency at different wavelengths, but also it's the jitter, it's the timing and accuracy of the superconducting nanowire detectors, which gives you a big advantage in terms of how quickly you can run your links, the rate at which you can pulse your sources. We want to be able to convert wavelengths, because the wavelengths required to operate these memories may not be the same wavelengths which are good for sending over long distances or sending through the atmosphere. So actually doing this quantum coherent conversion of wavelengths is in a nice small space capable package is going to be a challenge. Heralding, this is this quantum non-demolition thing. Loading and extraction of your qubits in and out of memory, they always need to be improved. How to increase the storage times and fidelity. I mean, we are now getting up into the hours, so it means that we are basically in the lab. We've got the time, the quantum memory time required to actually operate these space quantum memories. It's just how do we actually put them to space? And this is the big challenge: is how do we run this in this parallel operation? How do you have many modes, millions of modes, so you can operate these quantum repeater links in parallel, and increase the efficiency and the rate at which we can actually generate long distance entanglement. Anyway, this is sort of my last proper slide. So the conclusion is that long distance QKD is going to be the precursor to a space quantum internet, right? Once we can get these long distance quantum channels going, we can overcome the problems of background rejection, of getting these quantum systems working reliably in space. Then we can go towards entanglement distribution and these quantum memories. There's a lot of interesting technology challenges around different components, different subsystems. A lot of it's not quantum engineering, it's just classical engineering. How do we go from trusted to untrusted node QKD and really get to this entanglement distribution? Not just for QKD, but for also other networking computers, but also these other applications we discussed about, like timing, sensing, astronomy, fundamental physics. And really, we do need these quantum memories and repeaters as a long-term prospect if we're ever going to build these large-scale networks. And this isn't just a scientific endeavor. There's a lot of commercial interest in how do we build these space QKD networks. So mentioned Craft Prospect, but also Spectral is another company in Singapore, and they have a mission to demonstrate entangled QKD. So obviously a lot of people I've worked with over the years, a lot of funders. And just to finish off that, I run the International Network and Space Quantum Technology. It's funded by the UK Engineering, Physical Sciences and Research Council. And currently we've got more than 50 members representing over 16 countries. And really it's to solve this problem about how do we get quantum technologies into space and ultimately develop the space quantum internet. And we had our first workshop a couple of weeks ago, and thank you.
Fantastic, Daniel. I think such a lot of ground covered there, and I think in terms of the obviously that there's a lot of appetite for more discussion moving forward, but I think when there's such a broad range of topics discussed at a high level, a low level, well, of course it should be a high level being that it's in space, but but I think a good place to start with this would be at that high level. And so obviously, we mentioned Quest, for example, in 2016, the kind of quantum space race that was then sparked. We've come up to where we are now, and took a brief look at what's next. And one of the comments from the talk, from your talk, was regarding the classic internet, and that perhaps a lot of the applications weren't fully understood or expected when the technology was being created. So I think from that side of things, I think it'd be interesting to get your view on what the most exciting potential applications could be for the technologies that we've discussed today.
Well, I think there are two strands. So what we can do at the moment is we can see where quantum technologies and quantum entanglement enhanced technologies, how they can improve on the performance of existing applications or devices, right? So for instance, if you look at, say, PNT or GNSS, position navigation timing, right? Entanglement has potential, and quantum communications has the potential of orders of magnitude better synchronization, better timing, better positioning, if we can solve certain problems. There's some classical problems about ionospheric delays and all those kind of things, but let's say we're talking about we can solve those problems. So there are applications where we can definitely say, all right, actually quantum technologies, the initial goal is to exploit quantum mechanics to improve the performance of existing applications. And that's the easy look into the crystal ball kind of thing, right? It's really the question about what are those things that we don't have any existing thing to look at, or existing application, existing market. Who would have thought, I don't know, Google Maps, I mean, mapping and stuff like that. If you even think 30 years ago, right, it wasn't really a thing, right? The only people who care about these things were like, GIS experts, or, obviously governmental and military. It was big applications there like that. But for the average person, when you said maps, it was like, something on paper, right? But now it's integrated in everything, our daily lives, right? Now maybe there are some of those applications where currently it's very niche, right? That there's a capability or a market or an application which, because the technology isn't widespread or the performance isn't at the level that allows it to be widespread, maybe there are those niche applications that are begging for some enhancement or enabling capability that quantum communications, networking, or quantum technologies in general allows you. I mean, as I say, it's very difficult to make predictions, especially those in the future, about the future. So it's sort of those things. We don't know what we don't know.
Yeah, exactly that, and that was very, very much a subjective question, and really looking to sort of spark some conversation. But I think with that, I mean, as you say, what we don't know, and it might be that things, as other things progress, things like off-world communication, navigation, timing, if we become a multi-planet species, the potential there, that obviously that we wouldn't use to the same extent at present, but things like that I think could be really exciting. And within the world, within the talk, though, we sort of mentioned communications, timing, sensors, and lots of other areas. And we see, if you take the second quantum revolution on world, it's almost the reverse of what happened in the last century, where you had things like transistors, calculators, lasers, and then computers came quite late on. And we seem to be in certain areas, looking to get the quantum computer without going through those preliminary stages. I appreciate the analogy is not exact, but it's still up. I'm just wondering whether when you look at applications in space, if you see a certain chronology in terms of what piece should be in place to enable the next piece.
Yeah, no, that's an interesting question. So as I was trying to allude to, QKD, I don't see it as the main application for these networks. I just think as they're the pathfinders. They're a way that in certain segments and certain niche applications there could be a market which motivates the development of this technology, right? The fundamental technologies that we need are the ability to establish reliable high-rate quantum channels between space to space, space to ground, or any two places on the Earth, right? Whether that requires quantum memories or direct transmission. So establishing that core underlying capability over which you then run, say, QKD or run quantum networking, whatever like that. So to get to that point, right, there are very basic building blocks we need to get in place, right? And I think QKD is potentially one way that we can motivate, at least in some areas. It's not a universal solution, but in some areas we can motivate the development of these building blocks. Now, conversely, if we look at the kind of applications widespread entanglement distribution could enable, such as, say, quantum sensing, right? So if you're able to network at the quantum level quantum sensors, then you can increase, for instance, say the resolution, or you can increase definitely increase the coverage, and yeah, possibly you could actually be more sensitive to certain things. So getting those quantum sensors into space in the first place, right, even if they're not networked, is obviously going to be a step towards networking them later on, right? So I see there are a lot of parallel developments where, we're trying to build the underlying networking infrastructure, the underlying quantum networking infrastructure. QKD is one way of that would build certain basic building blocks of that. I think the development of, say, quantum memory, quantum repeaters is maybe driven by this more general push towards untrusted QKD, but also to networking quantum information processing devices. And then there's the other applications which can operate without being networked initially or having the quantum communication channels. But once they are established and are working in space, then we can look at then networking those and then enhancing their capabilities. So this is sort of my view as to how we can attack the problem on several fronts rather than necessarily thinking of it as a linear development.
Yeah. Yeah, and I think I could sort of hog the questions for a long time, but obviously we have got a broad audience here. So as Helen mentioned in the chat, if anyone wants to ask a question, please do raise your hand and we'll invite you in. Yeah. Anna, I can see that you've unmuted and got your camera on. Was you waiting to ask a question?
Yes. It's kind of a detail, but these quantum repeaters, they require Bell state analyzers that will pick out which of the 4 Bell states you have, right?
Yes.
And are those devices available on any scale? In any way?
Well, yeah. So ideally, you'd have a complete Bell state projection where you would be able to identify 4 possible outcomes, and each outcome would correspond to one of the orthogonal Bell states.
Yep.
Now, in practice, the easiest way of doing a Bell measurement is to use beam splitters as well as single photon detectors. But if you're using linear optics, there is a no-go theorem which says that you cannot do a complete Bell state measurement. The best you can do is identify 2 of the Bell states, and then the other outcomes you just don't know which of the Bell states or the other 2 Bell states you got.
So then you just try again?
Sorry?
So then you just try again?
Yeah. So there's a 50% overhead in that, it only succeeds half the time. But you can always relate that to, say, a 3 dB loss on one of the channels, something like that. So it's not a critical failure because we're distributing the entanglement, and if the entanglement fails, we just try again. We're not risking the actual information, except if you're trying to do teleportation. If you're trying to do teleportation, then you do need a near 100% efficient Bell state analyzer when you're doing the initial joint measurement. But for entanglement swapping, a 50% probabilistic Bell state analyzer is sufficient.
Thank you. You seem to know the whole universe about this topic.
Space is a big place. Nicholas, we had your hand up next.
Yes, hello. I just recall that in one of the opening slides in your presentation, you noted that there could be potential for synchronized clocks using similar methods. And I was wondering if you could comment on if that's directly related to the same concepts of quantum key distribution that has been the focus of the talk.
So it's this paper here. Yes and no. I mean that you're exploiting the correlations that you have in these entangled states. So if you say you've got 2 identical atoms, then obviously their energy levels they're the same, right? 2 atoms of the same isotope are exactly the same, which is one of the advantages of atomic or ion-based qubits over engineered qubits, and that nature made atoms identical if they got the same number of protons and neutrons. The actual synchronization itself, you're using the fact that these things will tick at the same rate, but if you've got these entangled states, then the ticking rate actually is multiplied by the number of entangled particles. So we're not talking just about single entangled qubit pairs, but we can use what are called like noon states. There's a technical reason why they're called noon states, but basically they're very highly entangled multi-qubit states, and because they're multiple qubits, then entanglement means that they act as a much faster clock, right? So that means if they're spinning around much faster, then that means that they have greater resolution, right? They're more accurate, right? So imagine it's like if you're trying to measure a race, right? But if the second hand on your clock was missing, or your stopwatch was missing, and you only had the minute hand, then it'd be very difficult to time a race, right? Like a 100-meter sprint. Much easier if you have a second hand, or if you have a hundredth of a second display, right? So having these entangled states effectively give you much higher time resolution. So that's one thing. The other thing is that because we're using these entangled correlations, these have secrecy, right? We can make secret bits out of them. We can do quantum key distribution with them, and we use that property that we can then secure links. So the individual nodes, they can communicate through authenticated public channels, just like in QKD, and they can compare their measurements on their entangled states. And if an interloper tries to, for instance, spoof being part of the network, then their result will not correspond to the expected result had they been part of the entangled state that's shared amongst the legitimate parties. So there are actually several aspects how the entanglement within this this joint state of all these qubits can actually be used to enhance the timing and synchronization, but also enhance the security of this network.
Thank you.
And we did have Aurora's hand up, but don't anymore. So I'm not sure whether that was put down by the system or not. Aurora, did you still have a question?
No, he explained it. It was mostly related to higher order entanglements, and yeah, he went into it. Pretty much what I wanted to ask.
Fantastic, thank you. Mohammed, we've got you up next.
Yes, I want to know more about atmospheric scattering, absorption, and turbulence. So, could you recommend a reference that models the atmospheric scattering and absorption over free space channels?
Yeah, so the standard tool to model absorption in the atmosphere is called MODTRAN, M-O-D-T-R-A-N, which stands for Moderate Resolution Transmission, or the atmospheric, or whatever, something like that. It is a commercial program. There is a web-based version which allows you to do some limited tests, limited calculations. There are free and open source versions. There's a one called LibRadTran, L-I-B-R-A-D-T-R-A-N, LibRadTran, which is a sort of an open source version of that. They're not easy programs to use, I have to say. Now, for modeling of turbulence, there is an open source program called AO Tools, Adaptive Optic Tools, AO Tools. And so that's developed at University of Durham, I believe, mainly for astronomy. But a lot of this adaptive optics really did come out of astronomy. Obviously, there are other classified applications, but obviously the open source community, coming out of astronomy. So those are your two main sort of avenues. I mean, there are other ways of doing simulations of turbulence and things like that, but I mean, a lot of people just roll their own. So there's ways of simulating turbulence effects through phase screens and free propagation via fiber optics. So you could do it yourself if you do it in Python or MATLAB, if you want to really learn how it works. But if you just want to play around with it, then AO Tools is the way to simulate turbulence.
AO Tools or AI?
AO, so adaptive optics. So A for adaptive, O for optics.
Mm-hmm. Okay, thank you so much.
And I can see we're kind of coming to the end of the allotted time, but I know it sounded as though before we were open to run over a little bit. So Daniel, if you're okay with that, there are a couple of questions in the chat.
I'm happy to stay on for a couple of minutes. Yeah.
I have a question.
Yeah, hi, Itamar.
Hello, everybody. Wonderful talk. And I had actually two questions, but I'll start with the first. And this is, since entanglement is so fundamental and mentioned so many times here, I wonder if some of the techniques that you describe may be useful to decide which of the industry competitors approach, and there are different approaches, which is going to be the winner.
So we're talking about like the different
like Xanadu, trapped ions, chemistry, all those, and of course the other names, IBM, Google, and yeah.
It's certainly one of the critical criteria, right? So I'm sure lots of you are familiar with the DPhil criteria about what you need to build a quantum computer, and the ability to generate entanglement is certainly one of those key criteria in the DPhil criteria. Now, if we look at the various architectures proposed, like superconducting or ion traps or neutral atoms or quantum dots, there is always some method by which you can generate entanglement. Now, conventionally, this is done via some 2-qubit gate, a control NOT gate, or some equivalent. In some other architectures, it's actually done via post-selection and interference. So so they use a method which is very similar to this entanglement swapping, this Bell measurement of these two incoming photons. So you can actually say so for instance in NV diamond, what you can do is you can basically entangle the nitrogen vacancy with an emitted photon. And that emitted photon from 2 of these NV centers can be then interfered, measured, and then you entangle swap so that the 2 NVs are now entangled. And so this is one way of generating entanglement. So this is in contrast to directly interacting 2 qubits, say through, for instance, in a quantum dot, you may want to do nuclear spin exchange, right? Spin-spin exchange. So every single quantum computing architecture must have some way of generating entanglement. Now, I don't know whether it's the crucial criterion which you can actually decide against or for different architectures, but certainly it is a very, very important one. Yeah, later on, please. I'm on the midline. A couple of minutes.
So much fun. So I wonder if you will be kind enough to relate in detail, or to the layman that is sitting here in Toronto, how teleportation relates to the long distance entanglement.
So relates in 2 ways. So one is that teleportation is the way by which you can transmit quantum information, a qubit, between, say, 2 quantum computers separated by a long distance without risking that quantum information if there is loss on that channel. So if you try to send that qubit directly and there's loss on the channel, then there's a high probability that that qubit never arrives. So you've lost that quantum information, right? That qubit that had your quantum state that you needed to interface those 2 quantum computers, that's lost. And your computation fails and you need to start again. Entanglement allows you, if you're able to send entanglement, and it can fail most of the time, but as long as at one point, one point you actually are able to create entanglement between those 2 quantum computers, one quantum computer can then teleport using a classical channel to relay the measurement result, that quantum state to the other quantum computer. Right. So teleportation is used throughout quantum computers. So even internally, you can use teleportation as a way of routing information within a quantum computer. So for instance, let's say that you've got a large scale quantum computer and that you've got one bit of the quantum computer, you've got a qubit which needs to be somewhere else in the quantum computer. You could physically just transport that qubit, or you could swap that, you can just do swaps of that qubit along, right? But if there's a method by you're able to distribute entanglement beforehand, right? Say you've got in different bits of your computer, you've got entanglement here and here and here and here, and there are entangled pairs which link up all those different areas of your large quantum computer. Let's say that you've got a qubit in one bit that needs to be in somewhere else. Instead of actually physically transporting or swapping it so it gets over there, it can just be moved or transported a short range to where there's an entanglement store. It gets teleported to the other bit of the computer where there's the other half of the entanglement, and then it can be used. All right. So so that's one way. Entanglement can also be used instead of just used for transporting qubits around. Let's say that you've got a qubit here and a qubit over here, and you want to do a control not operation. Right? So control not operation is one of the basic 2-qubit gates in a quantum computer. Now, usually you would have to physically move the qubits next to each other, do the control not, and then move them back, right? But if you've got an entangled pair, a single entangled pair of qubits, you can actually use that quantum entangled pair of qubits in order to generate that quantum knot. Right? You can see that if you've got 2 entangled pairs, you could, first of all, teleport one qubit over to the other qubit, do the local control knot, then teleport back using the second entangled pair. Right? So 2 entangled pairs is sufficient to do what's called a remote 2-qubit gate. Right, and any 2-qubit gate you can do using just 2 entangled qubit pairs. A control not is special. Well, control not only requires 1 qubit pair, so you can just do local operations on this half of the entangled pair, this half of the entangled pair with the local qubits that you want to do control not, and then in the end, these 2 qubits have interacted, and there's a control not between that's like acted on those 2 qubits. They've never actually met. They've only met virtually using the entangled qubit that's shared between those 2 locations. So entanglement within a quantum computer actually is very powerful as an architectural device to allow you to do delocalized operations without physically having to move qubits around.
Thank you. A very rich answer to be studied further.
And we also we now have a couple of the people who were from the chat, so that's killed 2 birds with 1 stone. So Zeki, if you'd like to come in and join us.
Yeah, thank you, and thank you, Daniel, for such a great presentation. I have a quick question. So, are there any entanglement purification protocols tested for satellite repeater networks or downlink, uplink? You know, any kind of?
I think we're far away from that. So obviously, you need, well, you could do Procrustean methods for filtering to try to improve the entanglement fidelity of individual qubit pairs, probabilistically. I don't think anyone's done that. I think that so far the fidelity of the distributed entanglement has been high enough that they haven't needed to do that filtering step before doing any of their other experiments. If you want to do, more advanced entanglement purification, obviously you need more than 1 pair, at least 2 pairs simultaneously that you can then do, say, your local operations. And typically these operations are non-linear. They're operations which are very difficult to do using linear optics. I think you probably could do something or an inefficient version using some linear optics, but I think that for generally you need to have non-linear quantum operations to do these things with any kind of efficiency. So we're a bit far away from that at the moment. Obviously, this is purification, quantum entanglement purification and distillation is going to be absolutely required in a full-scale network, right? The raw qubits, raw entangled qubits that are being distributed in these communication links will not be at sufficient fidelity to be used directly for interfacing quantum computers. They'll need fidelities, with how many 9s, 5 9s, 6 9s. We might only be at the, say, 99 or 99.9% fidelity level on the actual raw qubits distributed over these long distance links. So some sort of purification or distillation process is probably going to be required. So I think it really gets interesting once we get even small scale quantum computers. When we get to the couple of maybe a few tens of qubits which can then be error corrected, and then you can do the kind of operations required for distillation and purification. So yeah, no, definitely something that we will need.
Thank you.
And next up, we had Ron, who also had some interesting questions in the chat.
Yes, I got two questions for you, Daniel. Great presentation, by the way. The first one has to do with quantum sensors. Earlier this year, I saw a presentation on a superconducting single photon detector. They sort of labeled it as a quantum sensor, but it seemed to me what its job was is to create a classical pulse whenever it got hit by a photon. I was wondering if you could share what your definition of a quantum sensor is, and then I'll have a second question.
Okay. Yeah. All right. So maybe I should define my terminology a bit better at the start. So conventionally, when people talk about quantum sensors, they talk about sensors whose sensitivity or accuracy or performance is enhanced through quantum effects. So an example would be a gravity meter, right? So if you want to measure the gravitational field, then what you can do is you can use a BEC, a Bose-Einstein condensate. You can split it in half. You can put it into an interferometer, and the interference fringes you see will be affected by the local gravitational field. And the accuracy that you could get, or performance you could get, could be enhanced compared to a conventional gravity meter. So this is what most people call a quantum sensor. It's something that senses but uses quantum effects to perform better. Now, a single photon detector, such as say the superconducting nanowired detector device or a silicon avalanche photodiode, we call them quantum detectors, I guess. They detect quantum states or quantum states, and then they translate a quantum state, forms a measurement, and outputs a classical result. So that would be what I would call a quantum detector. A quantum sensor doesn't necessarily measure anything quantum, like the gravitational field. We don't need to quantize it in order for a gravitational sensor to use quantum effects in order to get better precision or a better accuracy. But quantum detector is measuring a quantum state and transducting it, I guess, into a classical signal. I hope that explains sort of the terminology.
Yes, and just to extend that, so if a single photon detector were to be advanced to something that could not only detect a photon, but something about the state of that photon, that would be more in line with, or calling it a quantum sensor, I would think, right?
Well, so we sort of do that already. So like a polarizing beam splitter plus two photodetectors, single photon detectors, that measures the polarization of a single photon. So we're able to make a measurement of the polarization state of that qubit, so of that optical qubit, by basically taking some optical elements plus a photon detector.
Okay, great. And my other question is, I was trying to wrap my head around this whole satellite to ground station sending of entangled photons. And I understand when photons are entangled, they're created at the same time, and then they're coerced into traveling down what we call a laser beam to a ground station. And so what I'm trying to understand is, do they travel in parallel? Are they actually zooming down that pathway side by side? Do they arrive at the detector at the exact same time? And what's going on with them while they're in transit?
All right. So I just refer to this picture here, conveniently provided about Micius. So this inset is actually the source of entangled photons. So what we have here is what's called a periodically poled KTP, or potassium something, I can't remember, a crystal. So this is a special nonlinear crystal, which you fire a laser into it, and then like a say a 400, well, sort of like an ultraviolet laser, and that ultraviolet photon can be down converted into two separate photons. Each of those photons, if you add up their energies, those energies add up to the original photon. So energy is conserved. So these two separate photons generated from essentially splitting a single photon in this nonlinear crystal, these two photons are entangled. In this case, they're entangled in polarization. So if you measure one photon horizontal, then the other one you will find will be in its vertical state, vice versa. If you measure it at plus 45 degrees, one photon, the other one will be measured in, say, minus 45 degrees, right? So that's an example of an entangled state. So they separate the two photons using this polarizing beam splitter. So that means that photons of different polarizations will actually come out of different directions. All we know is that they're different polarizations, but we don't know the polarization of each individual photon, and that's entanglement, right? The state of one photon is actually inextricably linked with the state of the other photon. Overall, we know what the state is, but the individual states are uncertain in an intrinsic coherent way. And so these photons now are then sent separately. So this this output port is basically ends up in this telescope sent down here, and this photon coming down here is eventually comes out and sent down here. So they're generated at the same point, but then they're sent in different directions. Now, it actually doesn't matter whether they arrive simultaneously or not. In this experiment, they are measured immediately when they're collected by the telescope. Now, because of special relativity, if these two places they're what are called spatially, they're outside the light cone of each other, so they're spatially separated. So there's no frame of reference in which one photon is detected before the other, right? At least in certain configurations, certain geometries. So in that sense, you can say that both photons are measured without knowing at all what happened to the other photon, right? Because there's no way that a light limited signal could get from one telescope to the other telescope where the measurement result of one could go, or the measurement choices of one could go to the other telescope before the other photon was measured, right? So in that sense, the two measurements are simultaneous. It doesn't matter, actually. You could arrange it so that one photon was measured before the other, but it actually doesn't matter because the correlations are really interested in the state, not in the order in which they're measured.
Fantastic. And I think that is all of the questions from the audience. There were some interesting comments sort of supporting and working alongside that. So, Ron, I've just noticed you on mic again.
Yeah, I just want in what you just described, each one of the entangled photons is actually being sent in a different direction to a different target.
Yes, yes.
Okay. That was.
So these are these two beams represent.
Is there ever a situation where they're both sent to one target?
I don't know whether. I don't know when that would be useful.
Okay. All right. So I guess that was my misunderstanding. So it's two different targets. That's what's going on. All right. Thank you so much.
Yeah. So if I go back to this, so if I go back to, where is it? Yeah. So basically, what we have here is in the middle. There's the entanglement source, and then one photon goes here, the other photon goes here, and in the end, you've got these two entangled photons, which are one at Alice and one at Bob. But in the middle, there is the source, which is the satellite.
Yes.
Thank you. That helps a lot. Thank you.
Fantastic. Well, Daniel, fantastic talk. I think we've covered a lot of ground with the presentation, also with the questions as well. Oh, before I close up, Itamar, I've just seen you on mic.
Yes, thank you so much. I was wondering if, again, what we learned here today can be useful, and even the recent comment about one photon arriving before the other, that may hit on a big open problem in parallelism. Namely, sometimes a task depends on the previous task being performed. However, maybe some of these elegant tricks that we heard today can be useful to break this one.
Yeah.
And it's a theoretical question, not necessarily in quantum computing. You're just hovering over parallel computing.
Yeah, so there has been a bit of work on how parallel can you make a computation? In particular, how parallel can you make quantum computation? Now, this has been studied in the context of measurement-based quantum computing. So I don't know how many people are familiar with measurement-based quantum computing or cluster state computing. But essentially, you've got some massively entangled quantum state. And then the computation is driven by measuring a qubit, and then based on its measurement result, you adapt the measurement of the following qubit. And then in the end, the final measurements actually reveal the computation that you want to do. Now, in some computations, you can actually measure some qubits simultaneously, right? That the measurement, the type of measurement you make on one qubit does not depend on the result of previous measurement. Now, a curious idea is that, well, is there a way, or are there computations where you can just measure all the qubits simultaneously, right? They could be all measured differently, but potentially could they all be measured simultaneously, where the measurement that you do on one qubit does not depend at all on the result of measurements of the other qubits? So this is sort of a simultaneous or depth one quantum computation. Now, there are some interesting results showing that this is not universal, and there is but still it's quite powerful. This kind of computation on a massively entangled quantum state where you make all measurements simultaneously is still quite powerful, but not universal. So there are some very interesting intermediate quantum computational classes where you can reduce things to depth one. This is some years ago, so my recollections can be a bit hazy, but so there are certainly, I'm sure the field has advanced quite a lot, and obviously translated these results in MBQC into gate-based quantum computing as well. They are equivalent formally, so there's probably a translation between these two systems. So I think that the wider question, the bigger question is if you do have measurements in spatially separated regions of space, but are sharing a quantum, highly entangled quantum state, what are the kind of quantum information tasks you can perform? And actually, there has been some work about this, about how you can, like, for instance, how can you measure non-local observables in this way? Are there fundamental limits in terms of the the accuracy versus the probability of being able to do these kind of measurements? So yeah, the way that space-time is actually arranged compared to how we do measurements on entangled states is a really fascinating topic.
And in this vein, may I ask you about how to exploit this elegant concept that is called tunneling? Quantum tunneling.
Yeah, quantum tunneling. So yeah, let's say this is where we have a quantum particle can basically traverse a region where classically it's not allowed to be, right? So
yes,
like passing through a wall where it can't exist within that wall. Now there'll be some interesting experiments to try to test the speed of tunneling. I don't think I'm familiar enough with the subject to say anything definitive on it. Now there have been proposals to how to use this for improving the speed of communication or the efficiency and stuff like that. But I'm not quite sure it's very applicable to long distance communication. The problem is that tunneling usually happens in the near field, right? You're using the fact that the evanescent waves, and you can then use these the tail ends of these evanescent waves. There's still some probability that the particle can actually jump through the barrier due to the at long scales, at long distances. These evanescent waves don't really play a part in the propagation process. So it's a bit difficult for anything beyond angstroms or nanometers, unfortunately.
So can we revive the Schrödinger's cat?
Well, there's some very interesting quantum philosophy problems that people have come up with how if you're able to actually revive or have these revivals of these superpositions that you would normally would have collapsed.
Thank you.
Sorry, I cannot raise my hand on my end. Definitely it's my fault. The Zoom, for some reason, I don't know. Can I ask a question without raising hand? Yeah, okay, I open my mic. Yeah, thank you for your great presentation, Daniel, and apologize I joined late. You might have already covered before I joined. I noticed one of as you explained as well, one of your slides, about that stations. One station is using laser. So compared to photon, which can 24/7, but the laser will be can work only after dark, at night. So yeah, is that correct?
So the systems that have been demonstrated today typically only work at night. You are correct, because of the background light problem. We have to be careful in not having other photons come in and basically fake a signal.
So then, sorry. So then why that specific station using laser then? Why they still choosing laser as a...
Well, so a laser is considered to be a classical signal source, and we can't just use a normal laser to distribute entanglement. Now, even with these single photon quantum channels, there has been quite a lot of work to try to make them operate in daylight. And there's actually good demonstrations to show that. So one thing you do is you use very, very tight spectral filters. So the filters are sub-nanometer in wavelength bandwidth. You also use very narrow, very, very short pulses and short coincidence timing. So that means that in the very short period of time that you're expecting a photon, then it's very unlikely that an external photon arrives at that time. And the other way that you get rid of the background light is that you spatially filter. So basically, your telescope, which is looking up in the sky, you make sure that the detector can only see a very, very small bit of that sky, basically diffraction limited bit of the sky, which is where the satellite is sending the light from. And so this has actually been demonstrated. I believe the US Air Force Research Labs, they demonstrated this in the middle of a desert at noon, and they're able to show they were able to do QKD in the middle of the day, and in the middle of a desert, over a representative distance and elevation, which demonstrated that you could actually do this single photon quantum transmission even without even in the middle of the day. Now, that being said, there are other ways that you could perhaps do quantum transmission using sort of quantum states of light, which are sort of closer to a laser than what a single photon is, right? So these are what are called continuous variable quantum states. So continuous variable states are sort of like the states that you get out of a laser, but you can use nonlinear optical methods like squeezing in order to basically give them quantum properties that you can then exploit. So you can distribute entanglement using squeezed light so these strong beams, these brighter beams, could be more resilient to background noise, but they can also be more affected by loss. There are pros and cons of the different ways of trying to transmit quantum information. Either use single photons and say the polarization or the time bin, or you use continuous variables, which can be in principle bright, but can suffer from losses.
Thank you, and also thank John for moderating today's session. Thank you.
No, it was good to have you on board, and particularly if you couldn't put your hand up, so that's absolutely fine.
Yeah, I'll try to figure out my Zoom. I think what I'm using is older version. I need to update.
Yeah, no, it's good to have as many people involved as possible.
Thank you.
John. So I think that may be everything from the questions. So in that respect, first of all, obviously, Daniel, thanks for a wonderful talk and presentation and answering such a varied range of questions and topics. And for the people on the talk, I would suggest following Daniel and the work he's doing at Strathclyde University, and also with other partners. I know it's something that always fascinates me. So, I can imagine there's a lot of others that would feel the same. And alongside that, I think, the Washington DC meetup, obviously you're all aware of that. The link to watch again, if you haven't seen it all, has been put in the chat here. But I'd encourage everyone to come to future meetings as well. Deb and Helen are doing a great job of this. And obviously from myself, if people want to reach out and connect, my name is John Barnes, and for issues regarding workforce talent, ecosystem development and community, follow Entangled Positions. But first and foremost, once again, thank you so much, Daniel. Fantastic talk.
Yeah, no, thank you for inviting me along. I had a very very good questions, very good discussion, and a lot of people anticipated a lot of what I was going to say, which is always good.
Yeah, I think a lot of the things I was going to raise had either been dealt with in the talk or by people along the way. So
I'll just say I will send a copy of my slides to Helen to distribute afterwards. So yeah, thanks for those inquiries.
Thank you, and over to you, Helen or Deb.
Yeah, thank you, Helen. I mean, Dr. Oyi, and hope you come back again at sometime in future. And we really appreciate your talk and we'll distribute your talk. Okay.
Thank you for coming.
Mhm.
Yeah, fantastic as always, Daniel.
Thank
Hey,
you
John.
again.
John,
Alex,
I like.
Oh,
I just thought I'd say hello.
Oh, hi, Alex.
good to see
Great
you, Alex.
presentation, and really enjoyed it. It's amazing how much I learn every time I hear you.
Yeah, I mean, I've given variations on this talk in the past, but I thought I'd try to give a little bit more some of the nuts and bolts on the entanglement swapping and things like that. So,
Yep.
Because I thought that would be interesting to this group.
Yes, so AG's just messaged regarding the recording. It's in the chat, AG.
John, I want to do a meeting with you. Can you give me an email or something?
Yeah, bear with me 1 second. Let me just jump onto actually I can type. I'll grab my LinkedIn profile as well as my email so you can have both. So there's my LinkedIn. And I will also put the company page as well. Slide that. So I've just put in the my LinkedIn, the email, and the company page. People have commented on in between, so they're kind of sandwiched.
Okay, thanks.
Yeah, obviously thanks for everyone for joining us today. And yeah, Deb and Helen, I'll catch up with you both soon, and hopefully other people on the meeting.